Great. Well, I will begin with a word of prayer. So, of course, nothing was said before this as of a note. Anyway, Heavenly Father, we thank you for this day. I thank you again for these students. And I just pray that you help us use time wisely, just to understand a little bit more about basic point set topology. In your name I pray, Lord Jesus. Amen. So more or less we got to section 3.5 in Minetti. And I've talked a little bit about this before. Section 3.5 is on subspaces and immersions. What I want to talk to you guys about today is just briefly what's in that section, and then past that there's a section on topological products and Hausdorff, some basic properties of Hausdorff spaces. And then I'm hoping then that we will also talk about connectedness in chapter 4. My hypothetical target for today is for us to finish up through section 4.2. I shouldn't say that at the beginning because now it'll be depressing at the end when we don't get there. But oh well. What's done is done. By the way, maybe next Wednesday I can get the whatever you're going to do of those things I gave you guys. Just try to, whatever you want to do, whatever you think is interesting of that, just go ahead and do it and give it back to me. And then we'll try to start working out some problems in this book because man, there's a lot of interesting problems in this book I think are worth working. Okay, so do you guys remember the subspace topology? So if we have X, right, topological space, then if we have a subset of X is a subspace. In other words, it's a set given the subspace topology. What was the subspace topology? You guys remember?
It's the intersection of A with all the open sets in there.
Right. So let's say more precisely, this was X paired with the topology tau or whatever, and so the topology induced on A is just U intersect A such that what? U is an element of the topology on X. So that's the subspace topology. Now, the subspace topology, there's an important mapping that it makes continuous, the so-called projection map. The projection, wait a minute. Sorry, I'm already in the next section. Excuse me. This is a bad start. Can't even remember which section I'm in. No. I think I need a microwave with some. So, oh yes, the inclusion map, although sometimes people use like a Yoda, for this, but I'll use I. So I, which is a mapping from A into X, which is, just what? I of X is equal to X for all X and A, right? So the subspace topology makes this a continuous map, as we argued before, right? Before I put the cart before the horse, and then we went back and found all our cluster points and boundaries and such last time. But the time before last, we talked about the continuity of this, right? And we said that the subspace topology is it's the coarsest topology you can give to the subspace, which keeps this inclusion map being continuous. So there we go. Eventually it gets dry. You guys never use a microwave as a dryer?
No.
No, oh, you haven't lived. Let's see here. Soon you'll be in grad school and you'll realize all the things you can do with a microwave. You college students in your cushy dorm life, soon you'll be out in the world. Let's see what it's like. Oh wait a minute, you're already out in the world.
Yeah.
But let's face it, Michael insists on a certain level of comfort, and sophisticated lifestyle.
I mean, hey, like whenever we run our dryer, it makes the apartment like 700 degrees. So
Oh,
maybe
okay.
using the microwave, like it'd be more efficient and like it wouldn't make the apartment uncomfortably
But in the
warm.
winter, it's a good thing, right?
Well, no, like even now it makes it uncomfortably warm. Like it gets
Oh.
that hot.
Oh, I see. All right, I'm sorry. Let me get through this here. So then there's a number of propositions, which I just like to read for you guys today because I really want to spend the bulk of our time on connectedness. Proposition 3.5.4 says that, I always want to read, but I have to write. Sorry. So proposition 3.54, we have X and Z topological spaces, and Y a subspace of X, meaning it's a subset given the subspace topology. Right? Then, furthermore, we have F, a map from Z to Y, and a map and the map, changing the wording a little bit, the map I, I'm going to put a composed with here, composed with F. It's written IF in here. When I read this, I just read it as if, and it's really confusing because I'm an idiot. But so I compose with F maps from Z to X, and then the composite of F with the this is the composite of F with the inclusion of Y and X. And then he says if no, wait a minute. Next sentence, if I composed with F, it looks like if to me. If I composed with F is continuous, then what? Then also F is, and conversely. So what is this saying? I think I may have proved this last time we talked about this also. I'm sorry if I'm repeating myself. So let's see, here is a picture, right? I don't know why I'm doing that. Z, right? F goes like this, right? F is mapping to Y. Then what? Y is a subset of X, right? Right? So, the inclusion map, I suppose. Let me. The inclusion map, you could draw something like, I don't know, I think of it like this. Right. So I is a mapping from Y to X. But of course, you could replace, the range of the inclusion map is just Y again also. So the codomain X there is of course not, unless Y is equal to X, that's not a surjection. So what's this proposition really saying?
Inclusion maps don't affect continuity, and inclusion maps are continuous, essentially.
Right. With respect, of course, to the subspace topology. I think that's one way you could interpret it, yeah.
continuous function to the subspace, then you get a continuous function to the, I mean, that,
The space in which it's embedded,
yeah.
right? I think that's also right. Yeah, I like both of what you guys said. I think was good. I mean, another way of looking at it is when you're studying continuity, it doesn't matter if you take this, you know, the target space, let's say, whether you take it to be actually the range, or if you take it to be some bigger set, it doesn't change the study of continuity. So, which means we can be kind of cavalier as to what we take to be the codomain. You know, you don't have to be careful. Oh no, I made it too big. No, the continuity's altered. No, that would be weird. That's not how it goes. Which is nice. Right? So that's all right. Now, the proof of this is pretty straightforward. The forward direction, if we already have that this is continuous and f is continuous, then the composite of continuous maps is once more continuous, right? And then the other direction, if I have continuity, if I have continuity just of this, of the I composed with f, then if you think about the inverse image, I mean, I don't know, there's really not much to say there. If I look at the inverse image of an open set under f, then it would have to be open because I could just take the inverse image of that, of IF, which is open, but then, how to say it, I don't know, it doesn't do anything is the thing.
Because it doesn't change the inverse images, so.
Right, exactly, that's the heart of it. The inverse image of f is the same as the inverse image of IF, yeah. Lemma 3.55, we have let y be a subspace in a topological space X and A a subset of y. The closure of A coincides with the intersection of y and the closure of A and X. Try to write that down, draw a picture. Come on. Let's have marker problems. I'm going to get chalkboard before this. I'll tell you what. I'm going to have chalkboard here. You just wait and see. Let's see here. So y is subspace of X. Then what? A is subset of y. Then the closure of A in y coincides with what? Intersection of y with the closure of A and X.
Does coincide mean they're the same thing, or they have a non-empty intersection?
I think coincides means they're the same thing. Yeah. Like we use that word in another place to study the coincidence set of two graphs, for example. It's where they're matching.
Okay.
So I think that's it's a not too often used word, but that's the meaning. What was this lemma 3.55, right?
Yeah.
So again, we're in Manetti, lemma 3.55. So so there's different. You understand the notion of closure is what? It's the intersection of all closed sets which contain a subset, right? So the universe of all possible closed sets. If we think about X, right? Here's X. Here's Y. Okay, I'll just try to explain this by a picture. And then inside here, of course, you got A, right? So the closure of A in Y is something like, you know, you think about things like this, and things like this, and so forth. And you think about all of those things, you know.
Those are all subsets in the subspace topology.
Right, these are all
subsets in subspace topology.
yeah, closed in the sense of the topology, the subspace topology of Y, right? So there's that notion of closure of A. And so I could maybe call this whole thing the closure, sorry. Some notation might be helpful here. Say closure sub Y of A, right? And what he's saying is that's equal to the closure, I can't spell closure today. So just today, I don't know, let's do closure in X of A. They coincide. So
intersection of that Y, right?
oh, right, I'm sorry. Exactly, because
There could be closed sets.
where is A? A is taken to be a subset of Y. Huh. It's gotta be some, it's hard for me to see with my picture why that needs to be.
Well, the closure of A in X doesn't necessarily have to be in Y.
Closure of A in X. Oh, right, so that's, essentially the point is if I had something like that, right?
It's kind of hard to imagine with two-dimensional, I think.
No, I think you got it. So like this point right here. Suppose that's outside Y. Okay. Then the closure of A and Y wouldn't contain that point because it's outside Y.
Right.
But the closure of A and X would contain that point. But if we intersect with Y, then the closure of A and Y won't contain that point. So yeah. But this is nice because this means that we can sort of unambiguously refer to closure of a subset with respect to the subspace topology. Nothing too weird happens. All right. The proof is like 3 lines, but I'm going to go on here. Lemma 3.5.6, if X is a topological space and Y is a subset of X, and Z is a subset of Y, then we've got these three relations. I need more space to write these out. Okay. So lemma 3.56. So we've got, let's see which one's the biggest. X is the biggest. Let me draw a picture. So here's X. Inside this is Y. Y is a subset. And then what?
It's 4:00 p.m.
Quiet. Let's see. Inside this we have Z. All right. So that's the story here. X is a topological space, Y is a subspace, and Z is a subset. All right. And then these are the results. Number one, if Y is open in X, let me say Y is an element of the topology in X, then Z is an element of the topology in the subspace topology on Y, if and only if what?
It's an element of topology on X.
Yeah, Z is open in X. So Z is an open subset of Y, if and only if Z is an open subset of X. Now that assumes what? That assumes that the subspace, which we're forming the subspace topology, is in fact open itself. That makes sense if you think about like obtaining a subspace topology from like the real line, say with the intersection of an open interval or something like that. Nothing weird happens with, you get fuzzy edges, so all the sort of pathological things you might imagine happening at the edges can't. If y is closed in X, I don't have a good short notation for that. Y closed in X, then Z closed in Y.
You could just say it's not an element of the topology, right?
Oh, no, but that's not,
Or is it?
the
No,
open,
that's not true.
I wish, it- no,
Yeah, you're right. It's close enough. So-
right, unfortunately, there's not that dichotomy. Let's see here. Z is closed in Y. Excuse me. Yeah, Z closed in Y. If and only if Z is closed in. All right, and then 3. If Y is a neighborhood of, if big Y is a neighborhood of Y. Neighborhood of, oh, sorry. Contrast of y, little y. All right, then, and Z is a neighborhood of y in Y, what? If and only if Z is a neighborhood of Y in X. What was a neighborhood of Y? That means that if we,
There exists an open set. It's containing y inside.
okay, so this Y is a neighborhood of Y means that there's some open set inside Y which is also containing the point little y. Yeah.
Do we have, was that the notation just I of y or I of x? Did we use that before?
Right, I think, yeah.
Okay.
Family of neighborhoods.
That was the family of neighborhoods, and then here.
Oh, that's not just.
And then here, more annoyingly than that, I would need a different notation for the family of neighborhoods in the
Why?
subspace topology versus the family of neighborhoods in the total topology.
Okay. It's not confusing.
But anyway, that's why you gotta make choices. Do you wanna use words or do you wanna use notation? And, I don't know.
I'm fine with words. I was just making sure.
Yeah. Which one let's prove one of these, you guys. Which one do you wanna prove?
2.
2? Okay. We will prove 2. So y is closed in X. So what do we get if y is closed in X? That means X with y removed is open. Open in X, right? So what does that mean? I'm just gathering data before I try to prove anything. That also means what? That means that that's it. Okay. Sorry, I was thinking something else, but that's it for now. Okay. There's what we have to work with, right? But then what are we supposed to study? We're trying to study this this biconditional, right? So suppose Z is closed in Y. Then what? In other words, what? That means that Z closed in Y means what? It means that,
Y minus c is
yeah. Subspace topology, right? So we're trying to argue that Z is also closed in X, right? So what does it mean for Y minus C to be in, what does this mean here?
Y minus c is the intersection of an open set x and y.
Right, so there has to exist some, let's say U in the topology of X, right? Such that what? Such that minus z is equal to u intersect y.
But y is
Uh-huh. What am I trying to prove? I'm trying to prove z is closed in x, right? So my goal is to show what at the moment I'm trying to, what I like. We need to show that x,
x minus z is open.
z is open, right? Be a little bit cooler. Yeah, but now it's dark. Man, win for losing. Keep going. I can't think without light. X minus z is open. How do we get that from math? Oh man, he's dismissed 1 and 2 as being trivial. You guys should have chosen number 3. We had a lifeline with that one. Trying to z closed in y. What does y minus z look like? It's sometimes pictures help. I don't know. So y minus z is this thing, right? And that's the intersection of what? Of some open set. So it's like there's some u out here, right? Like that, right? I mean, roughly speaking. I mean, certainly the intersection z intersect u has to be what? Is that right? Y, I mean, that z is a subset of y. Since z is a subset of y, if there was a point in this intersection, then that would mean you had a point which is in z in this intersection, but by definition that can't be the case. So I mean that has to be destroyed. So that's empty. Something.
I thought there might be some property of saying like x minus z is x minus y union y minus z or something.
Right. That's my suspicion is that I need to set theoretic lifeline here.
That's what we need here.
So how do I relate the set difference of x and z and y and z? Oh, you know, Surely this is true.
Y minus Z.
Equals?
I think so.
Should be.
Do you guys believe that just because I wrote, because of, you have faith in notation, or do you actually know this to be a property of sets?
I mean, we can prove it.
Assume this for a moment. Does that give us what we need?
Yeah.
Why does that?
C union of two open sets.
Oh, right.
Well,
Right. Because this is,
yeah. Well,
well, remember, well, the Y is closed.
Is that really not something we can assume though with the sets right there? Isn't that kind of? It seems kind of basic.
I don't know if it's true or not. I mean, it would be nice if it's true. It might be that it's a subset, or, I mean, I haven't thought through it. I'm not a card-carrying set theorist, you know. I don't, it's not hardwired into me. I had to work these things out or look them up. Man. Would that even be enough, though? I mean, oh, but Y isn't open. We're laboring under the assumption that Y is closed. So if I take the total set, the total space, and remove a closed set, what are we left with? Oh, I guess we might be left with an open set. Is that true? I mean, it's true in the sort of basic examples I can think of. If I take the real line, which is probably a bad place to gain intuition from for abstract questions of topology, but just for a second, if it doesn't work for the real line, we're in trouble. Certainly, if I take the real line and I remove a closed interval, I'm left with a union of open rays. And I think it's the case that, so if I know, let's think about this. If I have the whole set, right, and I remove a closed set, and on the other hand, I know that what is it, well, this has to be open, right? Oh, that's the definition of closed set, right? Oh, okay, so this is open. I'm an idiot. Why am I quibbling over that? This is open. That's clear. You guys told me that 5 minutes ago. What about the other thing here? How do I know that's open?
okay, so we can replace Y minus Z with U intersect Y,
Yeah.
right?
Okay.
And then is there a distributed property with like unions and intersections?
But Y is closed, even though U is open.
Right, okay. But can we, like, is a union, like A union B intersects C is A union B intersects, yeah.
So you're saying I've got something like A unioned with B intersects C, so there's some property here.
I think it distributes.
So A union B
intersect
intersect
B, or A union C.
A union C, like
Right.
that.
So,
But
let's see.
Yeah, you got it.
so then I would have something like,
Open.
so that would translate to X X with Y removed, unioned with Y with Z removed, right? And then what? Intersect with X with Y removed.
Wait, what?
Unioned with.
Well, I was thinking.
I'm sorry. I haven't.
Put, like,
Excuse me. I'm
U
sorry.
and
You
Y.
you want me to put U here?
Yeah.
I'm sorry. I was getting to it. And then this would be Y. Let me use some colors here. that.
Because the first one's going to be open, and the second one's going to be the entire X. So then we're just left with an open set.
Oh, right. Very good. So, and then it comes back to this.
I'm pretty sure we can prove that. That's
Pretty sure you prove that? Okay. All right. Well,
6 minus C.
you
is
take what
just-
I've written, union it with Daniel's faith in math, and then we got a proof. So, all of this is trivial, though. So, in defense of Minetti, it probably is if you have your head screwed on straight and are thinking about this in the right way. I've probably found a way to make it more complicated than it is. That is one of my gifts in topology. So, questions?
Yeah. It would probably be easier if we prove, like, if we use the first one and then
Yeah,
and then just use the same thing, but like with, I don't know.
that seems very likely if it's like many of the other things. All right, so let me get out of it here. The next, he makes a definition, a continuous one-to-one map, F from X to Y, is called a topological immersion if every open set in X is of the form inverse image of A under F for some open set A and Y. It's a topological immersion. In other words, a topological immersion is an injective map, which is a homeomorphism to its image. All right, so just the definition. We have F from X to Y. F continuous and injective in one-to-one. Said this is a topological immersion, or just an immersion since we're doing topology. In the study of other things, like say you're in manifold theory, you probably would add the assumption that it's a smooth map. You might say it's a smooth immersion then. But a smooth immersion is also a topological immersion. Okay, so like I said, if every open set in X, all right, is of the form of inverse of A for some open set A in Y. Like you said, put differently, F is an immersion if and only if it induces a homeomorphism from X to F of X.
So it's like almost it's everything about homeomorphism except onto.
Yeah, right. Yeah, exactly. So, in particular, good comment. Of course, if you have something that's almost a bijection, right? It just has the quote-unquote wrong codomain. You can obviously make it into a bijection by just swapping out the codomain, right? Let's call it F tilde. That's right. Then this is like tautologically a surjection, in that if F is a topological immersion, then this is a homeomorphism. See, because this condition makes the inverse. First of all, this condition makes it invertible.
Yeah.
From that, this being the domain of the inverse.
And the other condition makes the inverse continuous.
Right. So that's a topological immersion. Now, he points out not all continuous injections are immersions. Here's an example. He's like, okay, so if you look at the identity map from, say, the reals with the usual metric topology, Euclidean topology if you like, right? And if you go to that, to the reals, given the trivial topology, what's the trivial topology?
Metric. Oh.
So that's the trivial topology on the reals. He's like, okay, well, that is continuous, right? The inverse image, the inverse image of any open set is open, because there are only two inverse images to think about here. Everything and nothing, both of those are open. So the identity is continuous, but it's not an it's also one-to-one, right? That set theoretic is, you know, if you have f of identity of A equals identity of B, certainly it implies A equals B. But we definitely do not have the case that every open set over here, every open set over here is the inverse image of some open set over here. That's definitely not the case. So this is an example of continuous injection, which is not a topological immersion. What this means, guys, is that this notion of a topological immersion is what it's really saying is that if you look in Y, there's a copy of X, intuitively speaking. Like the existence of an immersion from one set into another, what it's saying is that, you know, there's really a copy of that topological set, the topological space X hiding in Y. And so the fact that this is not a topological immersion just goes to the fact that the reals with the metric topology cannot be found somehow hidden over here with the reals in the trivial topology. There's just not that structure over here. So, anyway. And then we can also talk about closed immersions. What's a closed immersion?
Is it an immersion that's a closed map?
Exactly. And an open immersion?
Immersion that's an open map.
Very good. I'm glad to see you did your required reading for this week, Nathan. Closed immersion. It's just what it sounds like. Okay. Enough said. Okay.
Okay, wait, what are open and closed maps?
Oh, I'm sorry. So a closed map, the image of a closed set is closed. An open map, it takes open sets to open sets. So, so saying a map is open, if the map happens to be injective, is equivalent to saying that the inverse is continuous. He has a little lemma here, which relates closed immersions and open immersions to a couple different simple conditions. This is lemma 3.59. F from X to Y continuous. Then 1 F closed and 1 to 1. Then F is a closed immersion. And 2, if F is open and injective, then F is open immersion. I will read you the proof of 1. He says, okay, assume F is injective, all right, continuous and closed. Then for any closed set C of X, the image F of C is closed in Y, right? And hence closed in the subspace topology of the image. therefore the restriction of f from x to f of x is continuous, bijective, and closed. Hence, a homeomorphism. You guys follow that? Maybe not. Let's sort through that just a little more carefully here. So let's assume f is continuous what is it? Continuous, injective, and closed. Alright? I'm trying to prove then that it is a closed immersion. Right? So let's see here. Well, it's already a closed map, that's given. So I guess we're really just trying to prove it's an immersion, aren't we? So what do I need to do? I guess I'll try to sort through his argument rather than think for myself here for a second. So his proof goes as follows. He says let C be a closed set of X then we have f of C subset of course, f of x subset of y, right, closed. And then he says that means that f of C is closed in the subspace topology of f of x. Do you see that? I guess that's the thing I'm a little bit shaky on here. F of C is closed in the subspace topology of this guy. I mean,
How do you know if a set is closed in a subspace topology?
right. Well, same as usual. So that it's closed. Being closed in Y means what? That means that. So we know this, right? Y with the set f of C removed is open in Y, right? So that means that Y with that set removed, right, intersect with f of x, right, is open in the subspace topology of the image. Because the intersection of any open set in the larger space with the subspace, with the subset gives an open set. That's the definition of subspace topology. Now I need to see that I'm trying to see this right now, right? Why is this true? I'm guessing it's set theory. So how can I simplify what I last wrote there?
Wait, so we'd be trying to simplify that to y minus f of c?
Let's see, this
Or f of x minus f of c,
right, I mean, this what we need is that f of x, right, minus f of c is open.
Right.
That's what I want. Oh. intuitively I can see that's exactly what this is. Like, think about this set. You have f of x, right? Here's a picture. Here's y, right? Here's f of x.
Which is open. Or is it?
Well, I don't know.
Oh, you don't know.
I guess it's closed because it's well, x
Well,
is
X
both
is closed.
x is both open and closed. So,
X
but
is closed.
Right.
So since f is a closed mapping, f of x is closed.
right. Now here's f of c. It has to fit somewhere inside f of x. I mean, that's the nature of
Yeah.
the image. The image is all possible outputs. F of c is a subset of those possible outputs.
Yeah. Can't we just use what we proved before? With the what we like, with like y close in x, then c close in y, if only if c close in x.
Well, probably I wasn't thinking about that. Come back to that in just a second. We're done with this argument, is my point, though, because if you look at this, right, if I take y and I remove f of c, right, and then I'm intersecting that with the image of x, right? So like this intersection throws out everything outside f of x, and then this removes f of c. So what you're left with is precisely this. This is that. Consequently, that's open. Consequently, f of c is closed in the subspace topology. But you saw a more orderly way to do it. We proved things about closed sets in the total space versus closed set in the subspace. We should use that theorem. I just forgot it. My memory is about 3 seconds long. It's sad. That's part of what makes topology hard for me. Is I don't.
There's a lot of stuff to remember.
I haven't internalized those theorems well enough. Yeah. I guess if I taught an honest to goodness topology course one semester, it might stick. I don't know. For a year. Ask me about something in the middle of number theory. I can't tell you at this point. You don't use it, you lose it, you know? Okay, so it's good? All right. All right, now that we're past the stuff I didn't want to talk about for more than 10 minutes. I think it was a necessary discussion we had in here. I mean, this is part of it, but I always want to go on to the next section. You know how I am. Oh, man. Oh. Son of a gun. Fine. I'm sorry. I should be where I am and do what I'm doing. I just have to accept that we're not getting to where I wanted to get to. Definition. Product topology. So the product topology, you take a pair of topological spaces, P and Q. You take their Cartesian product, and then you can put a topology on the Cartesian product. And his definition is rather nebulous, but it's a good definition. He says the product topology on P cross Q is the coarsest among all of those making the projections continuous. What are the projections? There's two mappings. The projection map little p from P cross Q to P, and little q from P cross Q to Q. I think you can tell me how they're defined. I mean, of course, as he points out, you can look at the power set on the Cartesian product, right? So there certainly exists topologies on the Cartesian product. And then he's like, and then you can just define these product what are these called? Projection mappings, and then you can ask the question of all the possible topologies on the Cartesian product, which is the most coarse, which is the coarsest for these projection mappings, and so he takes that as a way to define the product topology. So how does it work? It's pretty simple. P of xy is what? X. Right. And Q of xy. Y. Right. So the product topology makes these maps continuous, and it's the coarsest such topology. Now, I don't think that's how I defined product topology when I took topology. I think the definition I saw is part of this theorem, and the theorem has the following. This is theorem 3.61, page 58 of Manetti. He says if you take the Cartesian product of open sets, they form a basis called the canonical basis of the product topology. So one is that if you look at the set U cross V such that U is an element of the topology on P, and V is an element of the topology on Q, big Q. Let me give big P a foot so you can tell which one it is. There. I don't want you to get confused between my little p and my big P. So the Cartesian product of open sets, well this is a basis for the product topology. Okay. And what did it mean for something to be, what did it take for something to be a basis, remember? What does it take for something to be a basis for a topology? This is called the canonical basis, by the way.
Any open set, and it's going to be a union of elements of the basis.
Right, it covers the space.
Right.
And was that it? The definition was back on page 41. It says a subfamily beta of the topology is called the basis of the topology if every open set can be written as a union of elements of beta. Very good, yeah. Okay, so then 2, the projection maps are open. P, Q are open maps. And also, if you look at the restrictions, so you guys, I'll write the first one down, you guys can easily write the second one once I write it. So if we look at P Cartesian product with the singleton Y, for any choice of Y, to P again, right? What can we say about that map? And what can we say about this map?
Bijections.
Yeah, they're bijections.
They're homeomorphisms.
Yeah, greedier still. These are homeomorphisms, right? It's not particularly surprising that I tell you that, in fact, there are copies of the topological space P and the topological space Q sitting inside P cross Q in this way. In fact, lots of them. Because these are homeomorphisms for any choice of Y or X. 3, and this is really nice. This almost feels like advanced calculus, this right here. F, all right, a mapping from X to P cross Q is continuous. What? If and only if F1, which is equal to P composed with